That's really relevant. Forces. A couple of important things to remember about forces. Forces are vectors. What does that tell me about forces? They have direction. And forces, the units for forces are newtons, which are given the symbol of capital N. What is a force? A force is a push or pull. And that, if we think about pushing and pulling things, it makes sense that there is a direction, because you have to push or pull something in a particular direction. Now, because they are vectors, we can represent them like we've represented some of our our displacement vectors with a line and an arrowhead. So this is how we represent our forces. So this gives us an idea of the magnitude, whereas the arrowhead here gives me the direction. And this allows me to look at how more than one force can interact with another force. Now, think about our types of forces. As I said, we've got a push or pull. So there's the gravitational force. If I tied something like a lead weight to the end of a string, and I hold the end of the string, what is stopping the string, the lead weight, from falling to the ground? The string, but it's something about the string, because that string would just hang there without the lead weight. It's the tension in the string. So we can have a tension force. We can have other forces that we aren't in this section in the booklet, but we'll talk about them anyway. Do you know of a force that opposes motion? Friction? Air resistance. So we've got air resistance and friction. These always oppose the motion. So if my vector here that I drew up before represents the motion of a car, then I could say then that there might be some frictional force that acts in the opposite direction. Yep, so this could then be my frictional force, and it is opposing the motion. If it's, some questions will say that we're going to assume no friction, other questions will include friction. They are another force. We can have magnetic forces of attraction, etc. But we don't need to categorize all the forces, because in essence our categories are going to be incorrect. But if you go on and study physics, you will understand This one is a really important one. And this one is very important one. There's also like a spring force, and you will see this sort of thing also in elastic bands. So you know that if you stretch the string or the spring, or the elastic band, then it's going to pull back up again. Yeah, so that's going to push or pull on the object that's tied to the end of it. Now, this is a contact force. Here, this is an example of a contact force. Because this will only happen if we're in contact with those particles. We need to be in contact with the surface for friction, and we need to be in contact with air here, which is basically still particles resisting the motion, for this to occur. Whereas this one is a non-contact force. Because even if an object is not in contact with the ground or the centre of the earth, it's still going to behave, it's going to experience that force. For example, my book, the moment I let go of it, it's attracted towards the earth. It was already attracted. That force was always there. But I let go of it, I stopped applying my force, holding it up. And so it's there whether, no matter where it is, in reasonable proximity to the earth. But it's a non-contact force because it can act without there being those two objects in contact. Now, another thing to think about with our forces is if this, just say I am driving the car and this is the force that I applied. Okay, so I pushed down my foot on the accelerator and I'm pushing the car forward. And this is the vector that represents my applied force. We've already got the vector up there that's representing a frictional force. And we can add our vectors together like we did with our displacement vectors. And this then would be my net force. This is what I would actually see. Okay, because I applied this force to travel in this direction. Frictional forces opposed that motion. And that's how big they were. And so what we see, okay, so this is what we see, or this is the resultant force, is that one there. Because when I add these two together, this one is in the positive direction, this one's in the negative direction, and so it reduces the net force. If I had two forces acting together in the same direction, okay, if I had if this was force 1 and this was force 2, then my net force, what I would see, would be the sum of those two forces. So it just depends on which directions that they are operating in as to whether we're going to add them together or we're still adding them, it's just this one's negative. Okay. Now, at the moment I'm actually applying force to the floor too. But I'm not moving down because the force is applying the same force back up. So Another important thing to think about is another force that I didn't write was the normal force. Is if we think about somebody standing on the ground, and if we're drawing or if we're representing forces using a force diagram, which means that we need to draw vectors, we would normally draw our vector starting from the center of that object. Now, I'm just going to draw it to the side and say that this is then the weight force. That is my force that I apply on the ground. Okay, weight is a force. This is really important. Okay? When we weigh ourselves, or when we say, you know, if I say like I weigh 70 kilos, that's wrong. Okay? I do not weigh 70 kilos. What would I weigh?
Would it be 17 newtons?
Not 70 newtons, but we're on the right track. It's got to be in newtons because it's a force.
The times multiplied by gravitational force.
Yeah. So if we're going to round it, I'm just going to round it to say 10. Then I would say I weigh 700 newtons. Okay, because I've had to multiply my weight by the force of gravity, gravitational acceleration. Sorry. Yeah.
Then what if you're weighing in pounds? You say I weigh 70 pounds. Do you just...
Well, pounds are a measure of weight, aren't they?
So what if you have different measurements of weight? And
Yeah. So remember though that for our measurements we are using SI units. Pounds are not an SI unit. Yeah. So this kilograms is a measure of mass. So, okay, we say that I actually weigh 700 newtons. I have a mass of 70 kilograms. If I go into outer space, I'm still going to have a mass of 70 kilograms. Okay, my body mass, barring any dietary issues, is going to stay the same, isn't it? I'm going to be 70 kilos if I'm standing on Earth, or if I'm standing on the Moon, or if I'm on the International Space Station, 70 kilos everywhere. I'm 700 newtons when I stand on Earth, so that's my weight here. But if I'm in space, if I'm on the ISS, I'm going to be weightless. My weight will be 0. I still have a mass of 70 kilos. And if I'm standing on the Moon, I'm still going to have that 70 kilos of mass, but my weight will be 1/6 of 5/6 after. I can't remember which way around it is. Or less anyway. I'm pretty sure it's 1/6 of the what it is on Earth. Okay, so there's a difference there. We have to remember that weight's a force. And so if I think here that that's my weight force, well, because I'm not falling through the floor, there is an equal and opposite force, which is the normal force of the floor pushing back up on me. And because these are the same size and opposite directions, then F net is 0. Okay, for there to be a net force, there has to be motion. And if I'm standing still here like this, there's no motion, so there's no net force. That means that the forces are balanced. It doesn't mean that there are no forces, it just means that the forces are balanced. Okay, now how about, I'm going to push really hard on the board. Am I applying force?
Yeah.
Yeah? But what's happening?
There's an equal opposite force.
Sorry?
There's an equal and opposite force.
An equal and opposite force. What happens if I push harder again?
She's back to the same.
Is it pushing back? Is the force staying the same? The force back from the board, is that the same as it was when I wasn't pushing as hard?
No.
Why not?
If it's not equal, you would have moved.
Okay. So, at the moment, while I'm not touching the board, no force back from the board. I push, push, push. The force back from the board keeps going until, if I was strong enough, I could push the wall over.
So Sue, what actually happens in that instance? So like, because Newton's third law is what states like the equal and opposite reaction sort of thing. So when you actually push that wall over, there still has to be an equal and opposite.
If I managed to push the wall over,
Yeah.
then my force ended up bigger than the wall's force back.
Yeah. Okay.
I won in
Yeah.
the end.
But isn't there supposed to be always an equal and opposite?
Well,
force?
it depends on where you're looking in the system.
Okay.
And so, if we're looking at only parts of the system, then one can win.
Okay.
Yeah.
And if you push the
But if
wall
we
over,
look,
and if you push the wall over, we'd probably call you Hulk.
yeah. Now you can try pushing the person near you. Okay. Now you're going to push on them, and they're going to have to push back, aren't they? If they don't push back, then they move, don't they? Okay, it's time to push Jack.
Push my chair.
You don't have to push him off his chair. You can just give him a little slight shove.
Oh wait, no, I've got this thing behind me. I'm not going anywhere.
What about if you push your own hands? So hold your hands together. One hand pushes. What happens to the other hand?
It
What's
moves
the other one
away.
than the other?
Moves away. What happens if they both push against each other? Stay in the same place.
Isn't one hand going to be stronger than the other though? Eventually.
Okay, so we're now, we are definitely applying forces. We're pushing out on our hands. And so there are forces present. But if our hands don't move, then they have to be equal and opposite, don't they? Okay, but if I stop pushing with one hand, then I move it, and there is a net force. Does that make sense? All right. Okay, let's have a look at the booklet. Let's stop here now. Okay. So in this case, when I was stationary, there was no net force, but the net force can also be zero if the object is travelling with constant velocity. Of course, it would be handy if we talk about Newton's laws first, but doing it in the order it's in the booklet. Because this is a subset. This is Newton's first law. We'll talk about that later. So, our forces are balanced if the object is stationary or moving with a constant velocity. If the object is accelerating, then it's under the action of a force. There is a net force we can see. Okay? Does that make sense? Or yeah.
What would be an example of that?
An object travelling with constant velocity.
Yeah, like with no net force, like what would that look like?
Well, if, just say, we're going to think about somebody who's on an ice skating rink. And their friend has given them a push, shoved them from the side. Okay, so they're just giving them a shove, and this person is just going to keep travelling along the ice. Eventually, like, it's not perfectly frictionless. They're going to travel for quite a long way before they actually stop. So the moment they got the shove, a force was applied at that moment. But then once the shove is over, they keep moving with that constant velocity, even though there's currently no applied force in that direction. There's still the weight force and the normal force, because they're not falling through the ice, but the forces are balanced in that direction. Yeah? And now, after the shove is finished, they're still moving with a constant velocity. There's no net force in that direction either, because once the force application has ended, there's no force anymore. Yeah, but we still have motion here. We should try it. We just need some ice.